Now it's time to see why radians are useful, and why when we're talking about rotation we actually want to talk about angular variables instead of the linear variables we normally talk about. So to see why, let's take an example. Let's say we have a CD, and let's say we scratch a line across it. Okay, and then we turn the CD player on. It's broken, so it only turns just a little bit, just part of a turn. So it turns some angle theta. Okay, and let's say we want to take a look at two different parts of this CD. So we have one point we'll say is right here, and if we look at its path while the CD was turning, it would look something like this, right? It would be an arc. It would end up back here. If we look at a second point a little bit further out, we see that it would also have a path that's an arc. It would end up here, but it would still be in line. If you drew a line from, you could connect both of the points and the radius in both cases. So it's both, in a certain sense, kind of, we would say, like turned by the same amount, right? They've been changed by the same angle theta. Okay, but let's take a look at the difference between the distances, right? So we said that if we're using radians, we see that the distance we've traveled is theta, and we'll call this distance little r. So S of r is theta times little r. The distance to the further radius, we'll call this big R. So the distance that big R travels is theta times big R, and of course we see that we can just look at it and see that that's a bigger distance for big R than for little r. Okay. So now let's say we look at the time that it took for it to spin this amount. Okay, so let's say that it spun that amount, that distance, in a time t. So the velocity for the inner point is equal to theta times r divided by t. The velocity for the outer point is theta times big R over t. So we see that the point on the outside is moving at a faster velocity. And that makes sense, right? Because they're traveling in the same amount of time, but one of them has a further distance to travel, so it's traveling at a faster velocity. So every different point we have along this line is going to change by a different distance and by a different speed. So it doesn't really make sense if you have something that's rotating to talk about the velocity of its rotation, because every point on it is rotating with a different velocity. It's moving with a different velocity. Okay, but let's see what they do have in common. So notice, let's say we rewrite this angle theta, and we say that theta is equal to the distance d over the radius. Okay, so it's a distance over a radius. And then let's say we let theta change in time. So d theta dt is equal to, well, the radius of one point doesn't change as it goes along this curve. So the radius is the same. So you still have the 1 over r. The distance does, right? So we have the change in the distance with respect to time. But this is really just the velocity, right? So if we look at the inner point, we say that theta is equal to SR over r. So d theta dt is really the velocity of r over r. Well, this is just equal to theta over t. Similarly, if we look at the further away point, we see that d theta dt is the velocity of big R over big R, which is also theta over t. So we see that it's the same in both cases. So we define this quantity omega, where omega is equal to d theta dt. And omega we call the angular velocity. And you can see why, because this is the rate that the angle is changing. And for a rotating object, this makes more sense, because we can say that that an object is traveling with a certain number of degrees or radians per second. And as we mentioned in the last video, we usually consider degrees unitless, so essentially we consider radians unitless. So what this really means is that the units of omega are 1 over time. Right, so this is a frequency. So the angular velocity is really a frequency. Right, but we can change the angular velocity. And so if we let that change in time, we see that d omega dt is the second derivative of theta with respect to t squared. And that, again, is just 1 over r times the acceleration. In other words, that's ar over r. And we see it would be the same for the other theta. So we define this quantity, d squared theta dt squared, which is d omega dt, as alpha. And alpha we call the angular acceleration. So in other words, we can connect these now by saying that omega is equal to the velocity over the radius. We can say that alpha is equal to the acceleration over the radius. So now we have a way to connect our angular variables to any point on the circle, on something rotating in a circle, depending on its distance from the center where it's rotating.